You said earlier that to understand the entropy of a black hole, we must understand what's going on in the center of a black hole. And we all picture black holes as extremely chaotic objects, but as you mentioned, they're at the same time extraordinarily dense and compact. And one understanding I have of entropy is that one measure of entropy is that the more ways some configuration can be arranged uh, microscopically without affecting the appearance of the macro state, then the more entropy it must have. Yet when something is so tightly compacted, there are far fewer possible microstates in which the configuration can be arranged. So I'm wondering if you can help me understand where my picture of this is wrong, because on the other hand, I also understand that because black holes have no hair, they're essentially indiscernible macroscopically. So we might also think the opposite, that no matter how they're arranged microscopically, they result in the same macro state.
Yes, so general relativity would tell you that all of the matter that falls into a black hole eventually gets squeezed up to such small distances, almost at the center of this black hole, into a point. And so you would hardly see anything of where the matter is sitting. And you might say all this information that you have sort of thrown into the black hole can be a diary or a telephone book when we were used to that. I mean, there's a lot of things you can throw into a black hole and that all disappears. But what Hawking and Bekenstein told us is that this information actually kind of is stored on the horizon. And one way of thinking about it is even that if we are looking at how things are disappearing behind the horizon, when we look at it from the outside, actually, when we look from the outside, we don't see everything falling really through the horizon. We see it falling towards the horizon, because if something falls into the black hole, the clock that this observer or this object would have would actually start slowing down. And actually it slows down to such a point that we don't see it really disappearing behind the horizon. So from our perspective, everything that we throw into the black hole actually is just hovering actually very close to the horizon, and it's all there. But the reason we don't see it is that the light that it's emitting cannot reach us anymore without being sort of redshifted. I mean, that's what happens also in gravity, is that the color of light also changes. Because the clocks go slower, we don't see the light anymore that's being emitted. So it's almost black because it cannot emit light anymore that we can see. And so everything that is thrown into a black hole, you can also think about as actually being sort of put on the horizon and it stays there. And so what Hawking then tells us is that eventually all that information also has to come out. And the amount of information associated to everything that goes into the black hole is precisely proportional to that sphere on where everything is sitting. And so what we have learned indeed is that you have to look more closely, first of all, what happens near the horizon, but also think about a black hole as different than just all the particles that sort of had disappeared behind the horizon. It's really more about the information that's stored on the horizon. The other thing that I want to say is that also in thermodynamics, by the way, you see information kind of disappearing. If we describe what happens in a room, if we associate the gas in a room with, well, what we call a thermal gas, then we give it a temperature, we give it a pressure, and we have very little numbers that we need to describe that. And then all of the rooms with the same temperature and pressure kind of feel the same. So we don't see the microscopic information either. We know it's there if you think about the molecules, but if you just think about the gas, that gas just has very little things we see about. And so black holes are sort of similar. We only see the mass, we only see the charge and the angular momentum, but indeed we can also see a temperature. But those are the microscopic numbers that we see. The microscopics of what is really happening close to the horizon, we don't see from the outside if we are just normal humans or some observers that only look at the gravity, for instance.